Hello, and welcome to the lecture for Chapter 4 from OpenStax Astronomy. In this chapter, we're going to talk about the Earth, the Moon, and the sky. So, the world around us. Okay, so taking a look at this fish-eyed view of Earth from outer space, we see that Earth is a sphere. This is so important and so much we talk about, and of course, something we take for granted. But much of our understanding of the rotation of Earth, its behavior with its seasons, all of that is based around it being a sphere, a tilted sphere, a sphere that's in orbit, that's rotating around its own axis, and has a moon. And all of this, all these spherical bodies, all of this rotation, it's all about circular motion and, of course, spheres. Okay? So, one thing we want to make sure that we're clear on is how we quantify locations on this sphere we call home, Earth, okay? Well, it's all about latitude and longitudes, okay? You've probably heard of them. So we have the equator, right? So the equator is a logical point that is exactly halfway between the two poles, because here we have a north pole and we have a south pole that you can't quite see in this image because essentially the sphere is tilted towards us. Okay? So that equator is a measure of latitude. Latitudes are measured up and down between the poles. And again, they have a natural midpoint because the rotation of Earth is actually around this axis, an axis that runs through the poles. It's very much like a model of Earth, a globe that has a metal bar between the poles, and you spin it around that metal bar. In the case of Earth, there's no such metal bar, but there is actual physical rotation around a line that passes between the poles. Okay? Again, equator exactly halfway between. Now, that equator has a particular value of 0 degrees latitude. Okay? And then, therefore, we could go in steps of 10 up to the North Pole, which would be positive 90 degrees or 90 degrees north, okay, in terms of its latitude measurement. Now, we also do the same thing with longitude, which are lines that run through the poles rather than in circles around them. And the longitudes, there's no natural selection for a midpoint because there's no such thing as a start and stop as there are with the north and south poles. So the longitudes are more arbitrary in that respect. And we choose to label one as 0, which we call the prime meridian. It happens to pass through England, and that's just due to the historical reason and England being a world power when it was defined. Okay, so that would be 0 degrees in terms of the longitude. Okay, and then we can find any location on Earth defined as its latitude and longitude. For example, Washington D.C. would be something approximately on the order of 40 degrees north latitude, and looks about maybe 65 degrees west, 65 degrees west on the longitude. Okay. All right. Oh, and actually DC, there it is, 38, so not quite 40, and 77. So I was a little low on my approximation. Okay. And again, now I was just looking at the length of this arrow here, and each of these steps is 30 degrees. Okay, that's how I estimated something on the order of 60, but it's closer to 77, almost 80 degrees west from the prime meridian passing through England. Okay, and pretty close to 40 degrees north though. All right, so here is the prime meridian. All right, so it passes through Greenwich, England. Again, just an arbitrary choice. That's 0 degrees longitude. Okay, if you wanted to have 0 degrees latitude, you would go to the exact equator, right? And any point along the equator would be 0 degrees in terms of, in terms of the longitude, or excuse me, the latitude. Okay, now interesting thing to put this all into perspective is this demonstration or experiment called Foucault's pendulum. Some science museums throughout the world and throughout the United States have these pendulums built into them. The Foucault's part just refers to the name of the inventor that first made one, but they're just normal pendulum. What sets them apart from other pendulums that like you might see in a classroom is that this pendulum is very large. It's very large, as you can see, a very massive metal weight on it. The purpose there is that it has very little air resistance as compared to its mass, and so it will keep swinging for a very long time. All right. Now that The museums that have these do have to, occasionally give them an extra bit of energy to keep them swinging. But, back when they were first built a few hundred years ago, you could set one in motion and it would swing for weeks before it gradually slowed down. What's neat about this is as it swings for, say, weeks and gradually slows down before you have to give it the next burst of energy, it knocks over pegs that are oriented in a circle around it. And we can see in this picture at this location here, with the family watching, that some pegs have already been knocked down. Now, why does it knock down pegs, and why does it continue to knock down pegs in a circle? Well, that's because its rotation, or I should say its swing, is rotating. So at any given point, it's rotating in a particular straight line back and forth, but a few hours later, that line has apparently moved relative to the ground. So what's happening is its plane of rotation, so plane of rotation, is continually moving relative to the ground, or apparently moving. Now, what's actually happening is the ground is moving relative to it, because its plane of rotation is fixed in space. But of course, Earth is not fixed in space. Now, that, however, is a bit of an idealization or an approximation. Now, but let's clarify that and elaborate on it a bit. If you were to take one of these Foucault's pendulums and place it at the North or the South Pole, right? So the North or the South Pole, then it would truly be that the plane of the swing of the pendulum would be completely fixed relative to the Earth, and the Earth would be moving underneath the pendulum. Because at either of the poles, you have the Earth basically just spinning underneath it. Okay? There's no centripetal motion at the poles. There's just rotation of the ground underneath. And in that case, it would take a full 24 hours to make a circle all the way around, and all the pegs would knock down as that pendulum swung in its plane and the Earth rotated underneath it. Okay? Now, no one's ever built a Foucault's pendulum in either of the poles due to the harsh conditions there, but certainly it would work. Now, however, if you have one of these pendulums at any other location, it's a bit more complex. Now, we see here in the description of this picture that we're told it takes a course of 12 hours. Now, that is an approximation because it actually takes amount of time due to its latitude. If, for example, this pendulum was placed at the equator, it would actually not rotate at all relative to the ground, and two pegs would be knocked over, and no other pegs would ever be knocked over. Because in that case, there would be no apparent rotation of the plane of the swing of the pendulum relative to the ground, because the equator is not rotating, right? The ground is not rotating underneath the equator. Instead, the pendulum would be rotating with the ground completely, and it would just move around the circle of the Earth. At any other latitude between the poles and the equator, there's a certain amount of time that can be determined that the pendulum takes. The closer we get to the poles, so very high latitudes, for example, or very far south in the southern hemisphere, then it's going to take more and more time, approaching 24 hours. So where does this 12-hour approximation come from? Well, in northern latitudes that correspond to Central or Southern Europe, that's about how long it takes, although actually it's closer to about 13 hours. Okay, so there's the idea. Again, it could be calculated. Okay, so we define latitude and longitude. Let's think a little bit more about zooming out on the Earth and understanding the seasons. Okay, now it's good to have a picture of the Earth, including latitude and longitude, if we're going to talk about the seasons. But as I said, we've zoomed out, and now we're looking at a not to scale picture that includes the sun and the Earth rotating around the sun. Notice the arrows that show Earth's rotation around the sun. Well, one big thing about the Earth is you've got the axis of rotation, the very one that I mentioned is going to apply to the behavior of Foucault's pendulum, but that axis of rotation is not exactly aligned with our orbital plane, and that would be Earth's orbital plane around the sun. In fact, there is a 23.5-degree tilt of the planet. Okay, that 23.5-degree tilt is the reason for the seasons. So the fact that we have seasons on Earth, that the seasons vary mid-latitudes, so if on the equator, the seasons don't vary that much, but anywhere between the equator and the poles, there's noticeable variation in the seasons. The length of the day changes over the year, the amount of heat that gets trapped in the atmosphere changes over the duration of a year. Those are the seasons. The poles themselves also have seasons. They have very extreme seasons, but the point is that all of that is true, and all of that is because of the 23.5-degree tilt. If our planet had an axis that was aligned with the orbital plane around the sun, then we would not have seasons. The whole planet would have the same type of weather year round, the same day length year round, okay? Now we're going to talk a bit more about the solstices, the summer solstice and the winter solstice, which are named summer and winter based on how they affect weather in the northern hemisphere. Of course, the winter solstice in the southern hemisphere corresponds to the hottest time of the year. They still usually call it their winter, especially in somewhere like Australia, an English-speaking country. They refer to it as winter, but winters are warm, okay? Of course, in the northern hemisphere, we think of winters as being the coldest time of the year. But since we're going to talk about those more later, we'll come back to them, the solstices. I want to briefly mention the equinoxes right now. So the two equinoxes are points that are exactly between the solstices. So if we think of the entire year as being 360 days, that's the time it takes the planet approximately to take one full orbit around the sun. Well, then we have 180 days between the two solstices, and we have 90 days between a solstice and an equinox. There are two equinoxes, the autumn equinox, which is in September, specifically September 21st, and the vernal equinox on March 21st. Depending on the length of the year and the fact that we have an elliptical, not perfectly circular orbit, that they can actually vary between the 21st or the 22nd. But on the equinox, because the tilt of the planet now is neither away nor towards the sun, instead it's perpendicular, or it's in the plane of the sun, the entire day has or entire Earth, I should say, has a day that's 24 hours, or it's always 24 hours long, but it has a day of sunlight that's 12 hours long, and night that's 12 hours long. So the entire Earth experiences a shared day on either of the equinoxes that's 12 hours of light, 12 hours of darkness. And that's because the tilt doesn't orbit with the planet. You see that the tilt always points in the same direction, all right? You could think of it as always pointing to distant stars outside of the solar system. It doesn't point relative to the sun. It remains tilted the same way, which is why in the summer solstice, the tilt is towards the sun, and in the winter solstice, we see the tilt is away from the sun. But then again, that means that in the equinox, either of the equinoxes, the tilt is neither away nor towards, and the Earth has that equal length day and night. Okay? All right. So, to further understand the variation in the seasons, it's good to think about not just day length, but the way that the light gets spread out depending on where you are on the planet and whether you're being tilted towards the sun or away from the sun. So for example, in the summer, the sun appears high in the sky and the rays of the Earth hit very directly. Okay? So that means there's a certain amount of energy per square meter that's coming in from the sun. When that light hits the Earth, it's covering an area of just slightly more than 1 square meter. So there is not a large spreading out of that radiative light energy, okay? Because there's very much a conservation of energy, a principle of physics that's being applied here. Now, in the winter, on the other hand, the sun, is coming in, the sunlight is coming in at a very not steep angle because the sun is low in the sky, and therefore every 1 meter of incident sunlight, 1 square meter of incident sunlight, is spread out over greater than 2.2 square meters of ground. That means there's not as much energy per ground as there was in the sun in the summer. Therefore, it doesn't heat up the ground as much, nor does it heat up the atmosphere as much. So this idea of the angle of the sunlight contributes to warmer weather in the summer and colder weather in the winter. I say contributes because day length plays a role as well. Since the days are longer in the summer because the sun rises and sets and spends more time in the sky, then that just further adds to direct sunlight and more of it in the summer. In the winter, less direct and less of it. And that's why we have a heat variation between the summers and the winters, okay? Now, another interesting thing about the Earth's tilt is that we can think about the celestial pole and where it's positioned in the sky. Okay, now what is the celestial pole? Well, the celestial pole is just a projection of the Earth's rotational pole. So if we imagine the night sky as almost a painting on a sphere that's outside of the Earth, because that's the way it appears to us, then we can put coordinates on that celestial sphere that are the same as the coordinates that we have on the actual surface of the Earth, such as latitude and longitude and equator and poles. So we apply all that to tracking things in the sky. So therefore, the sky has a celestial pole. It's got a celestial equator. Okay. Now they're not real. There's no actual equator in the sky. There's no actual poles in the sky. It's just a way for us to quantify the location of, say, constellations, stars, and so forth in the sky. Okay? And again, it's just a projection of our own latitude longitude system that we use on the surface of the Earth. Now, when we think about some location on Earth, we can think about where the North Celestial Pole is. Well, the North Celestial Pole, if you're standing, for this little stick figure here, this person, if this person was standing at either the North Pole or the South Pole, well, specifically the North Pole, then the North Celestial Sphere would be directly overhead. In other words, the North Celestial Sphere would be at that person's zenith, the point in their local sky that's directly overhead. But if they're at some other location, such as somewhere in North America, then there's going to be a difference between where the North Celestial Pole appears and the North Star that happens to be located there, and the actual coordinate of north, and that difference is actually the latitude of the person, okay, in degrees. Now, that's a great way to find your location if you can locate the North Star. And you can also think about the sun's path through the sky. And this goes back to seasons. So in June, where we're in the middle of summer, we have the sun's path, and we see that it takes a path where it goes very high overhead. It essentially reaches the zenith of the local sky, and it spends a lot of time in the sky, right, with a very high path. In March, the path never gets, the location of the sun never gets as high. It's never directly overhead. So the sunlight never is going to be as concentrated on the ground as we were talking about. Its path is still fairly long. But as we get into December at the solstice, we see that the sun never gets very high at all. So of course now we have the sunlight spread out over a large area for every square meter of incident sunlight, and it doesn't spend that much time in the sky either because it's a short path. And so then that makes for very cold days in late December. Okay? And now let's just further look at this idea of the two solstices, starting with the summer solstice. So you can see in the summer solstice, the North Pole, right, which is located right there along the Earth's rotational axis. And again, we actually see this black bar almost as if we're imagining there's a bar running through the Earth. Of course, there's not, right? But we see that the Arctic Circle, shown here as this white line, or the North Pole itself, are facing towards the sun. They are getting 24 hours of sunlight. The sun never sets. We have a midnight sun for many, many months of the year, right at the North Pole. For almost 3 months of the year, the sun never sets, okay? All right, now the angle of the sunlight would still not be that direct. So although the sun never sets, there's not that much energy to warm up the poles because there's still that that idea of the square meter of energy. The sun never gets that high in the sky. It never sets, but it certainly never reaches the zenith. And again, you can just think of that in terms of the sun's location. It's going to ride above the horizon day after day up there in the, above the Arctic Circle. Okay, but still the sun doesn't set, and it does warm up a little bit. Okay, then we can see that we have, when we get down into a region between the Tropic of Cancer and the Arctic Circle, right, including all of North America, then we have days where there's a lot of sunlight, sun is very high in the sky, very direct sunlight. Okay, on the other hand, if we look in the southern hemisphere, we have indirect sunlight. The sunlight is getting spread out over a greater area. Okay, so for every square meter of incident light, it's being spread out over, up to or even more than 2 square meters of ground and air. The South Pole is in complete darkness. Okay, so whenever the North Pole is in complete light, the South Pole is going to be in complete darkness. The sun never rises in the South Pole. Months of complete darkness. Okay. And then if we look at the other extreme, we look at the winter solstice. Now the southern hemisphere is in summer. It's getting lots of direct light. The South Pole is having 24 hours of light. And now the North Pole is in its perpetual period of darkness for about 3 months. Okay? And we have short days and spreading out of light energy up in the northern hemisphere, making for cool weather. Okay? So those are the extreme examples of the two solstices, the summer solstice and the winter solstice. Okay, so enough about the seasons. Let's talk more about the motion of Earth. Now, certainly we've touched on the motion of Earth because we acknowledge that Earth rotates around the sun, and its tilt then is in a very, it's sometimes it's a point towards the sun, sometimes point away. Okay, that tilt of our Earth. But another consequence of Earth moving around the sun is a difference between two types of days, the sidereal day and the solar day. Okay, so what are these 2 days? Well, most of the time, the day that we talk about is the solar day. Okay, when people think of the day, this is the one that first comes to mind, because the solar day is how much time it takes to get back around to facing the sun. Okay, so if we think of a person here, this little orange stick figure, a solar day is the time to go all the way back around and face the sun. Okay? Now the thing is, to get all the way back around and face the sun, the Earth actually has to actually spin a little bit more than a full circle. Because a full circle, we could see, would not quite be facing the sun. We would be facing slightly away from the sun. Why is that? Because in the 24 hours it takes approximately for the Earth to make a full rotation, the Earth has actually moved around the sun. It's moved 1 degree. How do we know it's moved 1 degree? Well, because there's 360 days in a year, and there's 360 degrees in a complete circle. That's not a coincidence, okay? That's where that 360 comes from in terms of degree measurements of circles. It's because of the 360 days, okay? Now, historically speaking. So again, the solar day is the time to come back around and face the sun again, all right? So the solar day is that one there. So the solar day is larger than the sidereal day because the sidereal day actually refers to the time for the Earth to make one full rotation relative to space as a whole. We often say it's relative to the fixed stars that are outside of our solar system. We could also say if we just looked at the Earth as a spinning ball and we spun that ball in a full circle at a certain constant rate, well, then we would say, okay, we would, if it was in a laboratory, that ball was spinning, we would say, okay, then the ball to spin all the way around, well, that is the time, that's the period of a complete rotation. So a sidereal day is the period of a complete rotation. It doesn't care about the sun, right? The sun has no effect on the sidereal day. It's independent of the sun, you could say. All right? Now, the interesting thing about the sidereal day is it's always shorter, right? And it's relative to fixed stars instead of being relative to the sun. And it's about 4 minutes shorter, okay? So it's 4 minutes shorter than the solar day, okay? And the 4 minutes just comes from the fact that 4 minutes is 1/360th of 24 hours. So if I was to take 24 hours and divide it by 360, then I would get my 4 minutes. That's where that comes from. The fact that the sidereal day is 4 minutes shorter. Okay? All right. So we don't care so much about the sidereal day because practically speaking, we care for the sun to rise again. But it does have some important consequences on scientific research. Okay? Also, another thing about the passage of time is that, well, we have to decide where the day starts again. So just like the prime meridian is an arbitrary choice of longitude, at the other side of the Earth from the prime meridian, so about 180 degrees away from the prime meridian, is something called the international date line. And that's where we start days over again. The international date line doesn't exactly follow a line that's a longitudinal line that is 180 degrees opposite the Earth from the prime meridian, because people don't want it passing through countries, because you don't want to say have a city that has, that's split by different days. So it's meant to be passing through open ocean. But ships that pass over the prime meridian, or excuse me, the international date line, they have to change their their clocks by a full day. All right. So for example, if you pass in this direction, you jump forward a day, and if you pass in this direction, you go back a full day. All right. So forward and back. Okay. All right. And this idea of measuring the passage of time and coming up with ideas like an international dateline aren't just modern concepts. People throughout history have been trying to track time by measuring movement in the sky, movement of the sun and the stars, such as in Stonehenge and in the Americas here shown with Chichen Itza in the Yucatan, okay, from a astronomical observatory built by the Mayans. Okay, so enough about the passage of time. Let's talk about the moon, because there's a lot of interesting things going on with the moon. First, maybe we should take a moment to appreciate that Earth has a really special moon. It's a very large moon. None of the other terrestrial planets of the solar system have moons that are anywhere as close to the size of our moon. It's, it has dramatic effects on our tides. It's beautiful and captivating. And as we'll talk about in a minute, it happens to have the same angular size as the sun, which leads to astounding eclipses, especially in terms of solar eclipses. But we also have to understand its phases. And to understand its phases, we need to understand its motion. So if we consider that the Earth rotates around the sun, then we can think about the sunlight coming from this direction, from a very distant sun, because the sun is very distant compared to the location of the moon to Earth. It's a matter of it being over 200 times further to the sun than it is to the moon, right? So a dramatic difference in distances, okay? Now the phases of the moon include the new moon, the waxing crescent, and we're going to go here in counterclockwise direction because that's the direction of orbit, okay? The first quarter phase, the waxing gibbous, the full moon, the waning gibbous, the third quarter, and finally the waning crescent. Bit about the terminology. Waxing means growing, waning means shrinking. All right, so a full set of phases starts with new, goes back around, takes about 27 days, all right, or roughly 30 Earth days, to get back around to where it started and repeat the cycle again. All right, a new moon occurs when the moon is between the incoming sunlight, so between the sun and the Earth. On the other hand, full moons occur when the moon is on the opposite side of Earth from the sun, okay? And then all the other phases occur between those cases. Why would a full moon occur when the moon is on the opposite side of the Earth from the sun? Because at that point, the moon is reflecting all of the sunlight back to Earth, and we can see it clearly glowing with reflected sunlight. New moons, we can't see them because there is no reflected sunlight, right? Instead, there we see maybe a faint silhouette if we're lucky, and we'd only see it at sunrise and sunset. I'll explain why in just a second. But there's all the reflected light would get reflected away from Earth. And so to observe it, you would have to be in some space shuttle or on another planet or something in order to see that reflected light coming off of the face of the moon that's facing away from us, okay? Now, another thing is, since these phases of the moon correspond to locations relative to the sun, they also correspond to how the moon rises and sets relative to the rising and setting times of the sun. So the full moon rises when the sun sets, and it sets when the sun rises, okay? So that means that as soon as the sun sets, the full moon rises, all right? So if the sun sets at 9 p.m. on that day, then the full moon will rise right after that, okay? And that's because it's opposite us from the sun. That makes sense, right? On the other hand, a new moon rises and sets synchronized with the sun, which means it's completely washed out by the sunlight. So not only is the new moon have no reflected light, since the moon itself doesn't create its own light, the new moon is also completely obscured by the fact that the bright sun is in the sky at the same time as it. Okay? All right. So those are the phases of the moon as seen from Earth. Okay? Now, there's also this idea that the moon has one side that faces us and another side that doesn't, a visible side and the so-called dark side of the moon. Well, let's first clarify something. If we think about a new moon, and I mentioned this reflected side of light on the moon that we can't see, but a space shuttle could see or something, as long as it was outside the orbit of the moon. Well, this very bright side of the moon, shown right here, we can't see it as bright, but someone else could. But this side of the moon, on a new moon, is none other than the so-called dark side of the moon. So you can see right there that that term dark side of the moon can be a bit of a confusing term because clearly it's not dark all the time. All right. On a full moon, the side that we can't see is in fact dark. So sometimes the dark side of the moon literally has no reflected light because it's facing away from the sun. But what does that mean then? Why do we call it the dark side of the moon? Well, it's not called the dark side of the moon because it never receives sunlight. It's called the dark side of the moon because we can never see it from Earth. And why is that? Is that because the moon doesn't rotate? Quite the opposite. It's because the moon does rotate at a very specific rate. So let's consider what would happen if the moon didn't rotate, right? So of course Earth rotates. We've talked about that. It takes 24 hours or 24 hours minus 4 minutes for the Earth to make a complete rotation, independent of the sun, the sidereal day. Or it takes 24 hours for the Earth to make a rotation relative to the sun, the solar day. But the Earth rotates. Okay. Does the moon? Yes. And if the moon didn't rotate, look what would happen, right? We'd have one side of the moon facing us like this, and then later on we'd have a different side of the moon, right? Because now this side of the moon would be this over here, but we'd also have a part that we hadn't seen before that would have been obscured that we could see. And by the time we went all the way halfway around the rotation, then the side that was completely obscured from us when the moon was in this location relative to Earth now would be completely visible. So in other words, if the moon didn't rotate, we would see all sides of the moon, okay? Or if the moon rotated very quickly, we would see all sides of the moon. We would notice different craters, perhaps, throughout the night because we could see the moon, the moon's motion. But what happens is the moon rotates very slowly. It rotates so slowly that its rotation takes about 30 days. The same time it takes it to orbit. So in other words, the period of the moon's rotation is approximately equal to the period of its orbit around Earth. That's what leads to it always facing the same side towards us. And so we can't, from Earth-based observation, ever see the other side of the moon. We've taken pictures of the other side of the moon because we sent spacecraft up there and actually observed it, but we can't observe it from the surface of Earth at all because of the slow rotation of the moon and the fact that it's synchronized with its orbit. Well, we always see the same face. Now you might wonder, is this just a bizarre coincidence that the rotation of the moon exactly matches the period of its orbit? And by the way, this is uppercase T for period, common variable for that. Well, no, it's not just some strange coincidence. It has happened naturally due to the moon losing energy because it pulls on Earth's oceans. Those oceans pull back on the moon. The moon is much less massive than the Earth, and the moon has therefore lost energy over time. And that losing of energy has caused what's called a tidal locking, which is the synchronization between its rotation period and orbital period. Okay? So, on the topic of tides, let's speak a bit about them. Because I just said that the fact that the moon pulls on our oceans, and our oceans have been around for billions of years, and then the oceans pull back on the moon because that's physics, that's Newton's third law. You pull on something, it pulls back on you, and that has slowed the moon down, slowed down its rotation over time. But then that means also that our oceans get pulled on, right? It does, and it has a noticeable effect. All right, that creates the tides on Earth. We have the oceans rising and lowering over the day. All right, so the moon's differential attraction is shown on different parts of the Earth, right, more dramatically. So there's a greater pull on the side of the Earth closest to the moon, and a smaller pull on the Earth on the side opposite of the moon because it's further away. Okay, and that means the fluid in the oceans gets pulled on less on the opposite side. This results in two tidal bulges. All right, a tidal bulge on this side and a tidal bulge on that side. So in other words, there's a tidal bulge closest to the moon, and there's a tidal bulge furthest from the moon. Now, what's important to understand about these tidal bulges is it's not literally that the moon is stretching out the water on the side closest to it, and then somehow also stretching out the water on the side furthest from it. It's due to the fact that the water is a fluid and is freely flowing as it gets gravitationally attracted towards the moon. That's what creates the two tidal bulges. We have flowing away, shown in the arrows here, towards the bulge closest to the moon, and then we have flowing towards the bulge furthest away from the moon. A combination of a fluid process with a gravitational force. Okay, that's what creates the two tidal bulges. It's a bit complicated to understand that there are two of them, but it's important to accept that there are two tidal bulges, always one closest to the moon and one on the side opposite of the moon. Of course, our oceans are not incredibly deep like this relative to the radius of the Earth, right? They're rather shallow relative to the radius of the Earth. And of course, our oceans don't completely cover the planet. They're affected by continents. And so the tidal flow of our oceans and have to go through, different straits and past continents and through gulfs and so on. And that creates complicated tidal effects. Some tides are not the same over the whole Earth. Tides vary on different locations, right? Some parts of the Earth have very large tides, some parts of the Earth have rather small tides. But everywhere on Earth will have two high tides and two low tides for every 24-hour period, because the Earth is making that complete rotation in 24 hours, and essentially where you're located on the Earth will therefore pass through two bulges and two locations between bulges, which are the low tides. Okay, so every 24 hours, two high and two low tides. Okay, here's a place up in Canada that happens to be one of those places with very dramatic tides, right? So you can look how low the low tide is relative to the high tide. All right, and again, that's just due to the particular geography and topography of the planet. Now, the sun also affects tides. The pull of the sun is less than half as strong as the pull of the moon. Of course, that's because the sun is so much further away. Now, the sun is much more massive, over a million times more massive than the moon, but it's so much further away that the gravitational force is reduced. But it's still significant, and it's just under 50% as strong as the pull from the moon. And that means that when the moon and the sun are in a line with each other, okay, either during a full moon or a new moon, then we have spring tides, okay? Now, on the other hand, when the sun and the moon are at a 90-degree angle to each other, so they're pulling in opposite directions, then we have what are called neap tides, and neap tides are weak, because essentially the sun wants to create a high tide where the moon wants to create a gap between the bulges, and then so therefore the effects are reduced. The sun and the moon are fighting against each other in neap tides. And neap tides will happen during what phases of the moon? Quarter phases. So first and third quarter. All right, those are the phases of the moon that correspond to neap tides. Spring tides correspond to every full moon and new moon. Now you might be like, wait, but they're called spring tides. Does it mean they happen in the spring? Nope, that's just the term given to them for historical reasons, okay? But again, they correspond to phases of the moon, full and new, okay? So that's the combined effect of the sun and the moon on our tides, the movement of our oceans, right? Those fluids that flow around on the surface of the planet. Now, quite interesting, the fact that all these oceans are getting sloshed around and pulled on by the sun and the moon means that that's giving up a huge amount of energy. It takes a huge amount of energy to move those oceans around. And then energy has to come from somewhere. And it has to get dissipated and moved and changed forms. And think about all the friction that results in moving those fluids around. Well, that means the Earth is gradually losing energy, just like the moon lost energy to become tidally locked. And that means that over time, the Earth is actually slowing down, okay? And this was first proposed by George Darwin, who was Charles Darwin's son. And he came up with calculations in the mid-19th century about at what rate the Earth is slowing down. Since then, we've been able to experimentally determine with careful measurements that indeed the Earth is slowing down, right? So the Earth is slowing in its rotation. That means that the day is getting longer, all right? So the day is getting longer over time. As the day gets longer and the Earth slows, that is tied with actually the moon drifting further and further away, okay? Eventually, in billions of years, the Earth will have a day that is the same length as the lunar month. So in other words, the time for the moon to go all around the Earth will be exactly the same as the time for Earth to make one complete rotation. In other words, it's sidereal day. Now that's going to take around 4 billion years, and by then the sun will probably have become a red giant and destroyed the Earth, so it will never actually completely happen, but that's the direction that we are going. Now, that type of phenomenon is actually observed already. If we look at Pluto and its moon Charon, the planet Pluto and the moon are in that exact, well, relationship, where the time for the orbit of the moon to go all the way around Pluto is the same length as one rotational period of Pluto, one Pluto day. Okay? So that, could eventually happen for Earth again if Earth isn't destroyed by the sun. And at that point, the day will be about 43 times longer than it is now, okay, after billions of years. But it's a gradual effect, and over millions of years it'd be measurable, and it's at least noticeable, and it's measurable on just the order of years in terms of fractions of a second, okay? And it's due to the tidal effects of the sun and the moon pulling on Earth's oceans. All right. If we didn't have oceans, we wouldn't have this slowing effect. And by the way, this idea of energy loss gets tied in with the angular momentum of the planet and the idea that momentum as well as energy must be conserved. Okay, so now continuing to talk about the moon, we're going to talk a bit about eclipses because the moon and the sun lead to these amazing phenomena known as eclipses. And one of the big ideas predicated here is that it just so happens that the angular size of the moon and the angular size of the sun are equal, okay? And that leads to total solar eclipses like this one, where the moon completely blocks out the surface of the sun and only the atmosphere of the sun, known as the corona, is visible, okay? And a solar eclipse occurs on what phase of the moon? Well, only new moons, okay? That's the only phase of the moon that can lead to a solar eclipse, all right? And not all new moons do, due to an angular tilt of the moon's rotation relative to the angular plane of Earth's rotation around the sun. But there are plenty of times throughout the year where there's a eclipse season, and it's possible to have an eclipse, although it won't be visible on the whole Earth, okay? But regardless, every phase of the new moon is the only one that is a candidate, a possible candidate for a total solar eclipse. And the solar eclipse creates a small bit of complete shadow on the surface of the Earth that is around 60 to 100 kilometers wide. And that's because what's known as the umbra, which is the dark complete shadow of the moon, well, it's cone-shaped, and that cone gets rather small because of the distance of the moon from Earth and barely really makes it to the surface of Earth. That's why it's such a narrow shadow when it actually touches the Earth. All right. And of course, as we talked about, over time, as Earth slows and the moon drifts away, we'll get to a point where there are no complete solar eclipses because the Earth's shadow will terminate eventually, initially up in Earth's atmosphere and eventually well above the surface of Earth. And then that point, when the moon is between us and the sun during the phase of new moons, it will block out some of the sun, but not all of it. Right? There will be no so-called path of totality, which I'll mention again in a moment. Notice also we see Earth's shadow larger than the moon's shadow, but also this idea of the umbra being cone-shaped, the total shadow. All right, here's a picture of the sun's corona visible during a total solar eclipse, which is the thin outer atmosphere of the sun. Now, what are lunar eclipses? Well, lunar eclipses happen during full moons, all right? And that's when the moon passes through Earth's shadow, through Earth's umbra. And then we see that we have a moon that's completely behind our shadow, isn't receiving any sunlight, so it's not going to be the bright moon we're used to. Instead, it becomes a red moon during a total lunar eclipse because it's picking up the reflected light of all of Earth's sunsets around the perimeter of the planet. Okay, all that refracted bent light, which is red light due to only the longer wavelengths being able to actually survive through the atmosphere and not get scattered. The blue light gets scattered. That's why we have a blue sky, by the way. But that red light makes it to the atmosphere, and then that weaker light gets reflected off of the moon during a total lunar eclipse. So the moon is dimmer, but dramatically red. Now, here's this idea of the path of totality. We had a total solar eclipse back in 2017, where that 70-kilometer approximately wide complete shadow of the moon was cast on a path that crossed right across North America, making landfall around Oregon and then going back out in the ocean after it left South Carolina. And what's so amazing is we're going to have another one in 2024 that's going to take a path like this. All right, that's going to be in 2024. It's going to be another total solar eclipse passing through North America, and the last one in about 1,000 years. So if you're going to catch a solar eclipse in North America, 2024 would be the time. All right, well, that concludes our lecture on the sun, the Earth, and the moon, and just kind of a lot of visualization of the orientation of those bodies relative to each other, and some amazing ideas, I think, to think about and to kind of wrap your head around. I hope it has been interesting and entertaining. Thank you so much for watching.